Have a nice day, students. Welcome to Constitutional Chemistry. In this section, we are going to discuss the p block elements. The p block element in the modern periodic table, it starts from group 13 and ends in group 18. The metals are aluminum, gallium, indium, thallium, tin, lead, bismuth, polonium. Metalloids: boron, silicon, germanium, arsenic, antimony, tellurium, astatine. The non-metals: carbon, nitrogen, oxygen, fluorine, neon, phosphorus, sulfur, chlorine, argon, selenium, bromine, krypton, iodine, xenon and radon. The p block elements is very essential and important for the human life as it contains the oxygen. So in this section we are going to study the properties and the nature of the p block elements. In the p block element, the lost electrons, it will be enter in any one of the 3p orbital. As we know, the p orbital, it will have a 3 degenerate orbitals. So the lost electron, it will enter in p1, or that is px or py or pz. The p subshell, it will have a 3 degenerate p orbitals. This only, as we mentioned, px, py, pz. These 3 degenerate p orbitals, it can accommodate 2 electrons. In each it can accommodate 2 electrons. So totally 6 electrons it can accommodate. In each group of the p block element, it contains 6 elements. In group 13, 6, group 14, 6, like that. So here one example: boron, aluminum, gallium, indium, thallium, nihonium, which is not mentioned here, nihonium. As already mentioned that p block element, it starts from group 13 and it will be end in group 18. The atoms of elements of these groups receive the lost electron in the 2p, 3p, 4p, 5p based on the number of periods. If you move down the group, the p orbital, it will be vary. So here in the group 13, we can observe the lost electron, it will be enter 2p, then aluminum 3p, then gallium, the lost electron, it will be enter in the 4p, in indium the lost electron enter into the 5p. So the lost electron, where it will be enter, the element, it will be belong to that block. If it is entered in the p, it will be p block. If it is entered in the s, it will be s block. Electronic configuration. Electronic configuration of the p block element, the first element in the p block: boron, carbon, nitrogen, oxygen, fluorine and neon. This we can remember in one football player named Beknoff. The first element of the p block we can remember in one football player named Beknoff. The valence shell or electronic configuration, general electronic configuration of the group 13 elements, it will be ns2, np 1 to 6. Here the n, it vary from 2 to 7. The maximum oxidation state by the p block element, it will be equal to the sum of valence electron. For example, boron, atomic number 5, 1s2, 2s2, 2p, 1. The sum of valence electron in the second shell, the number of electrons, it will be 3. So the valency for the boron, it will be 3. So the maximum oxidation state of the p block element, it will be the sum of valence electron like this. Otherwise, we can take the group number minus 10. Boron group number 13 minus 10, it will be 3. So this we can call as a group oxidation state. So group oxidation state we can find by subtracting 10 with the group number. Besides group oxidation state, p block element, it will show number of other oxidation state. The group oxidation state of group 13 elements is +3. but plus 1 oxidation state, it will be more stable. If we take the group oxidation state in group 14, it will be plus 4, but plus 2 oxidation state, it will be more stable for lead, and plus 1 oxidation state, it is more stable for thallium. This trend this trend of appearing in the oxidation state 2 unit less, that means from plus 4 it's showing plus 2 as a stable, and in from plus 3 it's showing the plus 1 as a stable. The trend of showing the oxidation state by 2 unit less than the group oxidation state, it is said to be inert pair effect, and this become more prominent as we move down the group. So we want to know what are the inert pair effect. Now we will discuss the inert pair effect. In the elements of the 4th, 5th and 6th period of the B block, which comes after D block element, that means the D block element, it will be entered. The electrons, it will be entered in the D block and F block also. The electrons which is present in the intervening D and F orbitals, as we know, the D and F has poor shielding effect. Due to the poor shielding effect, this D and F, the electrons which is present in the D and F, it will not shield the S electrons which is present in the outermost shell. So the S electron, it will be attracted by the nucleus very tightly. Due to the poor shielding effect, the nucleus, it can attract the S electron very tightly. So the electron which is present in the S, it can't leave that much easily. So the electron in the outermost shell, that means in the P, we can remove it. Due to this, the oxidation state, it will be reduced from plus 3 to plus 1. So the electron which is present in the S, it will not involve in the bond formation. This principle is said to be inert pair effect. So from this slide we come to know the inert pair effect. It is happening, the S electron, it is held by the nucleus due to the poor shielding effect of the electron which is present in the D and F. Due to this, we can't remove the S electron, so it not involved in the bond formation. The electron which is present in the outermost shell, that means P, it can lose electron and it will show that oxidation state. If it is 1 means plus 1, if it is 2 means plus 2. The other oxidation state which is showed by the B block elements. So from this table we come to know what are the general electronic configuration for each group. So 13th group NS2 NP1, 14th NS2 NP2, 15th NS2 NP3, 16th NS2 NP4 and 17th NS2 NP5 and NS2 NP6. If you remember the 13th group, you no need to remember all this one because it is like increasing order. NS2, NP1, NP2, NP3, NP4, NP5, but NS2 it is common for all the elements in the P block. Then the first member you can remember by using the football player name Beknoff. And the group oxidation state you can remember by subtracting 10. By subtracting 10, you will get the group oxidation state. Then other oxidation state, we will discuss why it is appearing. So 13 plus 1 it is appearing due to the inert pair effect, and plus 2 it is appearing due to the inert pair effect, and plus 3 that is less than 2, less than the main 2 unit less than the main oxidation state, it is appeared due to the inert pair effect. So here also plus 6 means 2 unit less than plus 4, it is due to the inert pair effect, and plus 7 means 2 unit less than plus 5, it is due to the inert pair effect. The same thing in the plus 8 also. Other oxidation state in the special condition it will be attained. Chemical behavior. The P block element is the only one which contains the metals, non-metals and metalloids. The common metal among the P block elements like aluminum, gallium, indium, thallium, tin, lead and bismuth. The common metalloids, as already we discussed in the starting section itself, like silicon, germanium, arsenic, antimony, tellurium, while the other remaining elements it will be non-metals. The non-metals, it will have a higher ionization enthalpy. The reason, the size is small. If the size is small, it will hold the electron which is present in the outermost shell very effectively. So we can't remove the electron that much easily. So ionization enthalpy, it will be high. As ionization enthalpy high, the tendency of an element to attract the electron towards itself, the electron negativity also, it will be high than those of metals due to the smaller size. As it will gain electron, it has a nature to form anions. So the non-metals, it readily form anions because it is gaining electrons. The compounds which is formed by the union of high reactivity metals like sodium, and when it combined with the non-metals like chlorine, generally this type of compounds which is forming, it will be an ionic one, because here the loss of electron will be there and gain of electron will be there. So electrostatic force of attraction which will lead to the formation of ionic bonds. Compounds which is formed by the union of non-metals themselves, for example chlorine. If we take the 2 chlorine, it will be a non-metal. When it combine together, it's not going to lose or not going to gain. Instead of that, it will share the electron. The sharing of the electron which lead to the formation of Cl2. Here it will be covalent in character. Due to the small difference in electronegativity, this will happen. Oxides of nonmetals are either acidic, neutral. As we know, the nonmetals, it will be acidic in nature. The nonmetals, it will be acidic in nature. For example, sulfur dioxide, if you dilute it in the water, we get sulfuric acid. Nitrous dioxide, nitric acid. But calcium oxide, when you add it in the water, we get calcium hydroxide. So it will be basic in nature. So non-metals, acidic in nature. Metallic oxide, it will be basic in nature. Non-metallic oxide, acidic in nature, and metallic oxide, it will be basic in nature. So the next one, electropositive. More electropositive the metal. As we know, the metals, it have a tendency to lose electron. As it loses electron, it will get the positive charge. So it is said to be electropositive. As in the p block element, it contains metals also. So more electropositive the metal, the more basic its oxides. And more electronegative the non-metal, it will be acidic. Because electronegativity is the tendency of an element to attract the electron towards itself. So when it is gaining electron, it will get the negative charge. So the metals, it will be electropositive, and non-metals, it will be electronegative. As it oxides. The first member of each group of the p block element, it will be differ from the exceeding members. The first member of the p block element, Beknov, it will differ from the rest of the elements. Boron it will be differ from aluminum, gallium, and carbon it will differ from silicon, germanium. Nitrogen it will differ from phosphorus, arsenic. Oxygen it will differ from sulfur and selenium. The main reason for this, two main reasons is that one is size and other properties which depends upon the size. Because the first element in the p block, the size it will be less. And the absence of d orbitals in their valence shell. We will discuss this in the details. Size and other property which depend upon the size. In this, if you see, means all the first elements in the p block, it will have a small size. As already we discussed, if the size is small, the electron holding capability, it will be more. The electron holding capability, it will be more. Due to that, it will be high electronegativity. As it is high electronegativity, we can't remove the electron that much easily because the size is small, nuclear force of attraction, it will be more. Due to that, it will have high ionization enthalpy. So when you compare the rest of the element in the same group, this electronegativity and ionization enthalpy, it will be less because the size it will be more. The size it will be increases when you move down the group. Then absence of d orbital. The absence of d orbitals in the elements of the second period. So if you take the second period, if you take the boron, as we know the atomic number for the boron, it will be 5. 1s2, 2s2, 2p, 1. So we have the outermost orbital, 2s will be there and 2p in the 2px, one electron will be there, and there is no d orbital. There is no d orbital. Only s and p it will be there, and there is no d orbital. All other elements in the same group, when we move down the group, the d orbitals it will be present. Then maximum covalency. The first member of each group has 4 orbitals, as now we discussed s and p in the valence shell. So the bonding also, the maximum bonding it will be 4 only. So 4 pairs of electrons. So it can accommodate at maximum 4 pairs or 8 electrons. So the maximum covalency which is existed by this first group element, it will be 4. So the boron, it form only boron tetrafluoride. For example, the same concept, 2s2 and 2p1. This will be in the ground state. So in the excited state, the electron, it will be moved to the p. The electron will be go to the p orbital. Then here the element which is going to combine the fluoride ion by gaining the electron, it will give the electron and it will make a bond. So totally it can form boron tetrafluoride. The pentafluoride or hexafluoride is not possible due to the absence of d orbital. And the carbon, not only boron, carbon also it will form tetrahalides. The reason it have only d orbitals. It have only s and p, not d. Due to that, it will not form hexahalide or pentahalides. It will form only up to tetrahalides. The reason the carbon also is the first element in the p block. It doesn't have the d orbital. Nitrogen forms only nitrogen trifluoride. The reason, the nitrogen atomic number we know, it will be 7. 1s2, 2s2, 2p3. So if we take the outermost electron, 2s2, 2p3, 2s2 and 2p3. So the nitrogen, it can, the fluorine, by giving one electron, it can share and it will form a coordination compound like nitrogen trifluoride, and this will be this will act as a lone pair of electron. But phosphorus, it can form trihalides as well as pentahalides. The reason, the phosphorus atomic number, it will be 15. So 1s2, 2s2, 2p6, 3s2, 3p3. So if we take the outermost orbital 3s2, 3p3, we'll take the outermost orbital 3s2 and 3p3, and for the chlorine, 5 chlorine will be there, so it want to coordinate to the 5. But here in the phosphorus there is the d orbital. The availability of the d orbital is there, so the electron in the excited state, it will be transferred to the d. Now the chlorine, it will give one electron and it will make the, and it will produce the phosphorus pentachloride. Due to this reason, the phosphorus, it will form the pentachloride, and nitrogen, it will form only trihalides. The first member of the groups, it will be differ from heavier members in its ability to form pi-pi bond. So the pi-pi multiple bond, for example, if we take the nitrogen in the sp hybridization, you can see nitrogen sp hybridization. As we know, the sp hybridization, the outermost electron in the nitrogen, it will be 3. The outermost electron for the nitrogen, it will be 3. So one electron each, it will combine and it will form a sigma bond. One electron from each nitrogen, it will share and it will form a sigma bond. Then the other electron which is present, it will be act as a unhybridized orbital. The unhybridized orbital, when it overlap, it will lead to the formation of triple bond. it lead to the formation of triple bond. Like nitrogen triple bond, as the sp hybridization, it lead to the formation of triple bond. Not only nitrogen, even the carbon also, it will form the triple bond. Due to the non-availability of the d orbitals, this type of multiple bond formation, it will be take place. The coordination number in species of heavier elements may be higher than the first element in the same oxidation state. For example, if we take the nitrogen the first element in the p block, it will be plus 5 oxidation state, and phosphorus also in the plus 5 oxidation state. Both have same oxidation state, but the nitrogen it will show coordination 3 coordination, and phosphorus it will show 4 coordination. Now we will discuss this one. So here, as already we know that nitrogen the electronic configuration 7 1s2 2s2 2p3. So the outermost we can take 2s2 2p3, 2s2 and 2p3, and here 3 oxygen it is combining. So 3 oxygen, here the oxygen, the atomic number for the oxygen it will be 8. So 1s2 2s2 2s2 2p4. So 2p4 we can take it 1 2 3, and here it will be 4. So 6 oxygen like this. So 3 oxygen with the 4, 1 2 3 and 4, and again one more oxygen, 1 2 3 and 4. So as it want to make the bond, here it will gain one electron, it will become, here one electron gain and it will become O minus. So when it become O minus, here the sharing of electron it will make a bond, and here also one electron it will be shared and it will make a bond, and here also it will share one electron and it will make a bond, but here the electron which is not involved in the bonding, it lead to the formation of pi-pi bond, it lead to the formation of double bond. So the structure of the, so this is, we can call it the 3 coordination. So 3 coordination, the nitrogen, this is the 3 coordination with the pi bond. So the last electron which is not involved in the bonding, it will be over sideways overlap, it lead to the formation of pi bond. So the structure it will be like this. And if you take the phosphorus it will have a 4 coordination involving s, p and d orbitals. Phosphorus, as we know, 3s2 3p3. So 3s2 and 3p3, and we know that the phosphorus it will have that d orbitals also. So the number of oxygen which is coordinating, it will be 4. So here 4. So in the excited state, one of the electron it will go to the d, and here one electron it will be there in the excited state. Then when it make a bond with the 4 oxygens, the same process it will be continued, and here the coordination it involved s, p as well as d. Both it will have a same oxidation state, plus 5, and here the nitrogen also it will have a plus 5 oxidation state, and the phosphorus also it will have a plus 5 oxidation state, but the coordination it will be vary. Here the nitrogen it will have a 3 coordination because absence of the d orbital, but in the phosphorus there will be 4 coordination with the pi bond formation. In this section we discuss the p block elements, where the p block element it will be started group 13 to group 18. What are the important chemical behavior like inert pair effect, group oxidation state, how to identify the group oxidation state. and what are the unique nature in the p block elements like metals, non-metals and metalloids. It is together in the p block elements. So in the next section we will discuss the group 13 elements, students. If you like me, share and subscribe. Thanks for watching.